Hey, this is Mack Warren. I'm doing my Lab 3 on black holes. So the purpose of this lab is to calculate the mass of a black hole with a sun or with a star orbiting it by looking at the motion of its orbit. And in part 2, we're looking at the x velocity of a ship, but more interestingly, the orbiting velocity in the what if. This can obviously be extrapolated to looking at other celestial objects just in the universe and determining the mass of something that throws off sensors, maybe like a black hole when things are moving around it, so we can figure out how big it is. Um, Real quick, these are the results I got from part 1 and part 2 respectively. The mass of the black hole was really big as expected, and the speed needed to come close and not dive into the black hole was really big as expected. Here are the physical principles that we need to use. We need to use the momentum principle for obvious reasons. Things in motion have momentum, and we need that to look at how they'll move. Then the universal gravitation formula, because we're in space, those are the only forces acting on these objects. And then we have circular motion because these things are orbiting and moving in circles. Here's the part 1 code. We have mass and we have initial and final velocity. So calculating momentum, change of momentum, all that was relatively simple. Then with that, we can naturally get the net force and really the difficult part here was getting the mass of the black hole from that, but messing around with the equations we had, it wasn't too bad. Finally, we're printing on every loop the mass of the black hole because it isn't constant, um, at least super constant. So we need to average that to get the number we had here. So the system here was the star. The only thing we knew about it was its mass and, um, well, we did know its final velocity, but we don't really need to talk about that. The mass and the initial velocity. So with the knowledge of this motion and how it moves the orbit, we can calculate forces on it, as I explained previously, to get the mass of the black hole from that. Part 2, here at the top, we're going to first look at the ship's speed. This was obtained mostly through trial and error, though the ship X had to be sufficiently large, otherwise we would immediately get the crash into the planet error. I think it only even started working at like -2 E7. And then obviously it needs to go up a little bit to not run straight into the black hole. The second number was gotten mostly because I wanted it to scale somewhat similarly to the first number. Then we have the positions of everything that is calculated naturally by subtracting the positions. Finally, we have a whole bunch of gravity formulas that we had to put in, all relatively simple, all look the same because they are, and then add the two gravitational forces on each object to get the F net on that object. Obviously, we do technically have the planet as a system because we need to know how it moves to know how it affects the ship. So we do technically have that as a system of its own, but for the purposes of what we were looking at, really the ship's our system. Then obviously at the bottom we apply Newton's second law in the position update formula to figure out how it moves and how the velocity changes over time. The system here is the ship. The initial conditions that we knew were the velocity of that and the planet, the black hole mass, star mass, inertial positions. We aim just above the black hole, even though it is technically getting pulled towards it. It also gets pulled towards it with the force of gravity. And we got very close here, bent right around the black hole, and shoots away from it with the momentum that it has. The gravity isn't enough to pull back in. Rate of change can come directly from observing an object as it is calculable with purely the measurable quantities from that object. Basically what that means is we can just look at how it moves and, guesstimate what it weighs and get the change in momentum, or the range to change the momentum. And this is equal to the F net, but the F net difference mainly is that it comes from a bunch of components that we can't necessarily tell just from looking at an object. Particularly in the real world, there's air friction, all kinds of tiny, random little forces that we can't really know, but we can get the F net and then extrapolate the large ones from that. What if I did get a velocity that put it into a messy orbit, but an orbit. The left one is so you can see what it looks like a little cleaner, and then the right one is it over a lot of time. This is important because we do want to know how to get an orbit around an object. Um, and I know there is an equation to calculate that, but honestly, I just guessed.